Hey there again. This is the fourth abstract of the medical topic abstracts from NeurIPS 2022. We're looking at leveraging factored action spaces for efficient offline reinforcement learning in healthcare by Shengpu, Tang et al. And their summary is we present a simple way to incorporate action space factorization into offline RL reinforcement learning by learning linearly decomposable Q functions supported by both theoretical and empirical results. And their abstract reads, many reinforcement learning RL applications have combinatorial action spaces where each action is a composition of subactions. A standard RL approach ignores this inherent factorization structure, resulting in a potential failure to make meaningful inferences about rarely observed subaction combinations. This is particularly problematic for offline settings where data may be limited. In this work, we propose a form of linear Q-function decomposition induced by factored action spaces. We study the theoretical properties of our approach, identifying scenarios where it is guaranteed to lead to zero bias when used to approximate the Q-function. Outside the regimes with theoretical guarantees, we show that our approach can still be useful because it leads to better sample efficiency without necessarily sacrificing policy optimality, allowing us to achieve a better bias variance trade-off. Across several offline RL problems, using simulators and real-world datasets motivated by healthcare, we demonstrate that incorporating factored action spaces into value-based RL can result in better performing policies. Our approach can help an agent make more accurate inferences within underexplored regions of the state action space when applying RL to observational datasets. And they look at two healthcare scenarios, two healthcare use cases. Let me just run through their paper a little bit, and I'll point out that they look at the first is a sepsis simulator, and the second is sepsis treatment in Mimic 3, where they use a recurrent neural network with LSTM cells. And in their conclusion, I'll read that in a second, but just so you know that they provided links to GitHub and PhysioNet. The conclusion reads, to better leverage factored action spaces in RL, we developed an approach to learning policies that incorporates a simple linear decomposition of the Q function. We theoretically analyze the sufficient and necessary conditions for this parameterization to yield unbiased estimates, study its effect on variance reduction, and identify scenarios when any resulting bias does not lead to suboptimal performance. We also note how domain knowledge may be used to inform the applicability of our approach in practice for problems where any possible bias is negligible or does not affect optimality. Through empirical experiments on two offline RL problems involving a simulator and real clinical data, we demonstrate the advantage of our approach, especially in settings with limited sample sizes. We provide further discussions on limitations, ethical considerations, and societal impacts in Appendix A. Though motivated by healthcare, our approach could apply more broadly to scale RL to other applications, for example, education, involving combinatorial action spaces where domain knowledge may be used to verify the theoretical conditions. Future work should consider the theoretical implications of linear Q decompositions when combined with other offline RL-specific algorithms. Given the challenging nature of identifying the best treatments from offline data, our proposed approach may also be combined with other RL techniques that do not aim to identify the single best action, for example, learning dead ends or set value policies. And they have a slide deck that you can look at on the NeurIPS website, or you can find it there. And then here is their takeaway slide. Okay, guys, that's it for this one. We'll do another one on the next episode. Glad to have you. Take care. Bye bye.